Let's talk about percent composition. We've talked about chemical formulas and how to calculate the mass of a formula unit or the mass of a molecule. And that gives us information about the composition of a compound in terms of the individual particles. And that is very useful in many situations, but also knowing a relationship between masses of the different elements can be very useful too. And so percent composition is one measure that gives us information in that way. We use percentages a lot. You go to the store and they have a 20% off sale, or you have to pay a certain percentage of your income in taxes, or you land on that tax thing on Monopoly and you have to pay 10%, right? So we use percent all the time. It's a good idea to really understand what percent is. If you get the basic idea, the general idea of percent, you can figure out a lot of things. So in general, percent is equal to the part that you're interested in divided by the whole thing times 100. So if you had, like my oldest son's kindergarten class, there were 5 boys, it was 5 girls and 15 boys. 5 girls and 15 boys in his kindergarten class. Does that sound like fun? That sounds awesome. Craziness. So 5 girls and 15 boys. What percent of the class was boys? Well, we take the part that we're interested in. We're looking for the percent boy. So that would be 15. So we're going to take 15, and out of the total, how many children in the classroom? 20. 5 plus 15. So 15 out of 20, and then you multiply that by 100. 75%. So the class was 75% boys. If the class composition was the same, and there were 100 children in the class, then 75 of them would be boys. Okay, so that's what percentages are. We sometimes talk about the percent composition by mass of a given compound. And that's just a list of the percent by mass of each element. So the compound might have 2 elements, then it would be a list of, it's 25% carbon and 75% hydrogen or whatever. We can calculate the percent composition from the chemical formula, or we can determine it experimentally by measuring the amounts of elements in a given compound. Percent composition is an intensive property. That means it does not vary with the amount of substance. If you have a small chunk of sodium chloride, the percent sodium will be the same as if you had a room-sized chunk of sodium chloride. So it's constant for that compound. So when we talk about the percent composition by mass, we take this general percent formula and we make it specific to what we're interested in. The percent by mass of a given element in a compound is the mass of that element divided by the mass of the compound times 100%. This percent here gives us the units on the result as percent. Do not use the percent button on your calculator. Okay? That was something I never anticipated having a problem with, but some calculators have a percent button. Ignore that. That's for other things. That's not for chemistry. This percent here is just a unit. If you measure the mass of the element in grams and the mass of the compound in grams, the grams cancel out. You could measure them both in kilograms or in pounds or troy ounces or carats or anything you want. The units will cancel out times 100%. There's your unit percent. Okay? It's not the button on your calculator. Don't push that button. You'll get the wrong answer. Yes?
Did you say that if our units will cancel out when we do that, so we don't have to worry about that?
The units on the masses will cancel out.
Okay,
So the only important thing is that these be expressed in the same unit.
okay, we still have to worry about that.
Yeah, so they both have to be grams or kilograms or pounds or whatever. They'll cancel out. Okay, let's do an example. Let's calculate the percent composition of water. Here's a problem, and there's no numbers given. What do? We can't really do unit analysis, dimensional analysis here because we're not really converting units. We have to think about that percent composition idea. So the percent composition of water. We need to start with the chemical formula for water. What's the chemical formula for water? H2O. Right, H2O. So there are two elements. We're going to have two numerical answers. We're going to have percent hydrogen and we're going to have percent oxygen. So I'm going to be calculating percent hydrogen. That's going to equal grams of hydrogen divided by grams of water times 100%. The mass of hydrogen divided by the mass of the whole sample. It's the part divided by the whole thing. What do? There's no number given. I don't know how much water there is. Does the percent hydrogen in water vary with the amount of water that I'm looking at? No, the percent is the same. So I just need to choose an amount of water. You can choose any amount of water that you want. You could choose to do the volume of the Atlantic Ocean. That might be a little difficult. Or you can choose something easy. How about if we do 1 mole of this? 1 mole of water. Do we know how much 1 mole of water weighs? Could we figure that out pretty easily? Yeah, we could. So let's just choose 1 mole. Exactly 1 mole. Well, 1 mole of water, the mass of it's going to be the molar mass, right? So it's going to be 2 times 1.008 plus 16, and that's 18.016 if we don't round it all, grams is equal to 1 mole of water. Okay, so this equals the mass of the water is 18.016 grams. Because I just decided to say I'm going to do it for 1 mole. You could do it for 100 grams. You could do it for 1 gram. It's up to you. I'm just showing you what I think is the easiest. What's the mass of hydrogen in this amount of water? It's this part right here. As we were calculating the molar mass, we were also calculating the mass of hydrogen. Because it's the mass of hydrogen plus the mass of oxygen, right? So this right here is the part that goes on the top. So 2 times 1.008 is 2.016 grams of hydrogen. And then that's multiplied by 100%. Those grams cancel out. 2.016 divided by 18.016 times 100. Do not press the percent button. 11.19% of water by mass is hydrogen. Any questions? I put 4 significant figures there because each of these had 4 significant figures. And that was just based on the values I had for my molar masses for my elements. Well, what's the percent oxygen? There's actually two ways to calculate that. Well, let's just practice our percent equation there. The percent oxygen is going to equal what? The mass of oxygen divided by the total mass. It's the other part. It's the grams of oxygen divided by grams of water times 100%. Well, what's the mass of oxygen? There's 16 grams of oxygen in 18.016 grams of water. So 16 grams of oxygen in that 1 mole of water that I just, I chose to do 1 mole because I thought it would be simple. So 16 divided by 18.016 times 100. And I get 88.81% oxygen. So in any sample of water, 11.19% of it by mass is hydrogen, and 88.81% of it by mass is oxygen. When you look at the formula for water, H2O, there are twice as many hydrogen atoms as there are oxygen atoms. But the oxygen atoms are about 16 times heavier than the hydrogen atoms. So by mass, there's a lot more oxygen in water than there is hydrogen. The percentages, the percent composition of anything has to add up to 100. So the 11.19 plus the 88.81% should add up to 100, and in this case they do, and it comes out perfect. It's not always going to come out perfect, but it should be very, very close. Why might it not be perfect? Rounding. So I've rounded these masses here. And even if I use a more accurate, more precise periodic table and don't round them, there's still uncertainty in those masses. And so because of that, you can end up with it slightly different. But if you got 99.95%, you're probably fine. If you got 100.1%, that's probably fine. If they add up to 80%, you screwed up, right? That's not gonna be good. Any questions? Let's do another one. Example from the book. Lithium carbonate was the first mood-stabilizing drug approved by the FDA for the treatment of mania and manic depressive illnesses, also known as bipolar disorder. Calculate the percent composition by mass of lithium carbonate. When they say percent composition by mass, they want the percent of each element in the compound separately. Now, on a test question, I'm more likely to ask, what's the percent composition, or what's the percent by mass of carbon in lithium carbonate, and just have you do one piece of it instead of all of them. But here we're learning the process, and so we're going to do all of them. So they gave us the formula, lithium carbonate. So we've got lithium and carbon and oxygen. We're going to have 3 calculations here. And then we're going to see, we're going to get our 3 percentages, and we're going to add them up and use that as a check to see if they come out to close to 100, then that's a good sign. So again, I recommend choosing 1 mole as the amount because it's easier. So we'll find the mass of 1 mole of lithium carbonate, which is, determining the molar mass. And then we can use that for everything else. So, oops, did not mean to do that. Okay, there we're back. Okay, so 1 mole of lithium carbonate. We've got 2 moles of lithium, 6.941, and we've got 1 mole of carbon in there, 12.01, and 3 moles of oxygen. And here you really should write it out this way, because that's going to save you some work when you have to do the elements and find their masses. So 2 times 6.941 plus 12.01 plus 3 times 16. 73.892 grams. And we're using, just in general, we're rounding all of our things here to 4 significant figures. That's the mass of 1 mole of the compound. So the percent by mass of lithium in that compound is equal to what?
2 times 6.97.
Yeah, it's equal to the mass of lithium, which is this, divided by the mass of the whole thing, which is over here. And then times 100%. The grams are going to cancel out. Now, if you want to multiply that out and write it down, that's fine. I did the last one that way because I could multiply it in my head, but I don't feel like doing it on the calculator and writing the number down. So 2 times 6.941 divided by 73.892 times 100. And this gives me 18.79% lithium in lithium carbonate. And we're going to do a very similar calculation for the other 2 elements. So the percent carbon equals the mass of carbon divided by the mass of the whole sample, the mass of the compound. So the mass of carbon is 12.01 grams divided by the mass of the compound. So always the part divided by the whole times 100. And grams cancel out. 12.01 divided by 73.892. This gives me 16.25% carbon. And then the percent oxygen, mass of oxygen divided by mass of the whole thing. So 3 times 16. The grams cancel out, times 100%. %, oxygen. Now let's take those percentages and add them together. 18.79 plus 16.25 plus 64.96. Oh, that came out perfect again. 100. That's a good sign. Can you screw up and still have your percentages add up? Sure. So this 3 in here is the 3 from the formula. Okay? If you write out the calculation for the molar mass of the compound, it becomes much easier to see what you're doing. Any questions? So we can calculate the percent composition from the formula. We can also get it experimentally, and we'll talk about exactly how that's done. But the percent composition can be used to find the empirical formula. Remember, the empirical formula, empirical means from experiment. So this is determining the formula for a compound by experiment. And it's always the simplest ratio of the different elements. Doing a calculation like this, the individual steps are not hard. The hard part is just remembering the steps, the process. And so here's the list of things you need to do. So this is how to determine an empirical formula. First of all, you need to find the mass of each element in the compound. Sometimes in a problem, they'll tell you, oh, it had 5 grams of hydrogen and 25 grams of oxygen. Other times, you'll have the percent composition, and that's what we're looking at here, doing the empirical formula from the percent composition. Well, how do you do that? How do you get a mass out of the percent composition? Well, you say, well, I'm just going to say I have 100 grams of the compound. If I have 100 grams of compound and it's 25% carbon, that means I have 25 grams of carbon, right? So by choosing a sample size of 100, you can just directly convert those percentages into grams. So once you have the mass, then you calculate the moles of each element from the masses, and you just use the molar mass off the periodic table. And then we need to find the mole ratio. So you take all of those numbers of moles, you pick the smallest one, and you divide all of them by the smallest. That'll give you ratios. Now, sometimes they come out to nice whole numbers, other times they do not. If they're not whole numbers, then you have to convert the ratios to whole numbers. I guess there really should be a 5th step in there. Those ratios, the whole number ratios are the subscripts for the formula.
The mole ratio?
Yeah. The whole number ratio, mole ratios, are the subscripts in the empirical formula. So that probably didn't make a whole lot of sense. A lot of times that's how instructions work, right? You read the instructions, you're like, I don't know, let's start doing it. And then you start doing it, and then oh, I remember something about that. Then you go back and you're reading the instructions, and now they make more sense. So let's do an example. Determine the empirical formula of a compound that is 30.45% nitrogen and 69.55% oxygen by mass. So the first step in finding the empirical formula is to determine the amount of each element in mass, the grams. So here we're given a percent. So 30.45% nitrogen. If I have 100 grams of this compound, what mass of nitrogen do I have? What is 30.45% of 100? It's 30.45, right? So 30.45%, I can just change that to grams of nitrogen. You can do it other ways, but I really think this is the simplest. So I've got that many grams of nitrogen. How many grams of oxygen would be present then? 69.55 grams. I'm just choosing a sample size of 100 grams. So I have my mass of each element. The next step is to convert these to moles. We have to go to moles because moles is the counting number that we use, and the chemical formulas relate numbers of particles. They don't relate masses. So I want to convert to moles. So I want moles of nitrogen on the top, and I want grams of nitrogen to go away. Here's dimensional analysis poking in again. Well, how much does 1 mole of nitrogen weigh? Just look at the periodic table. 1 mole of nitrogen is 14.01 grams. So I've got 30.45 divided by 14.01. .17. If we're following sig fig rules, we should have 4. On these calculations, it is very important to keep at least as many significant figures as your numbers call for. Here, we're going to end up with whole numbers at the end anyway, and so keeping extras is better. You can use all of them if you want, but definitely do not round this off to 2. You're going to get in trouble if you do that. So 2.173, I'm going to add on the next 2, just for safety, and that's my moles of nitrogen. I'm going to do a very similar calculation with the oxygen. Moles of oxygen, grams of oxygen, so the units work out. I look at the periodic table. 1 mole of oxygen weighs 16 grams. So 69.55 grams divided by 16 moles. I'm sorry, 16 grams per mole. And I come up with 4.346. There's my 4 sig figs, and keep the next 2 moles of oxygen. Any questions? So those are the numbers of moles of nitrogen and oxygen in this compound. So I could write a formula, N 2.17345, O 4.34688. But that's weird, huh? Because you can't have 2.173 atoms of nitrogen in a molecule. We need whole numbers. And the way we're going to get whole numbers is we're going to find ratios. Okay? So we're going to take one and divide by the other. Well, we want whole numbers. We don't want more fractions. So we want to do this in a way that all of our ratios are 1 or larger. And the way to do that is you pick the smallest one. So I'm going to pick this number because 2 is smaller than 4. And I'm going to divide both of these by the smallest. So 2.17345 moles of nitrogen. What does that equal? 1. That tells me that the moles of nitrogen to moles of nitrogen is 1. Well, of course it is. It has to be. For every 1 nitrogen atom, there's 1 nitrogen atom. And then I'm going to divide this one by the same number, 2.17345 moles of nitrogen. This gives me the ratio of oxygen to nitrogen. 4.34688 divided by 2.17345 equals. Okay, this comes out to 1.99999. 1. And that's moles of oxygen per mole of nitrogen, if we're going to keep units in there. That is very close to 2, isn't it? It's not perfectly 2 because these are based on measurements and there is some uncertainty. But this is close enough that we can round this to 2. What this is telling me is that there are 2 moles of oxygen for every 1 mole of nitrogen in this compound. So I'm going to round this to 2. And those are going to be the subscripts. So this is the subscript for nitrogen, and this is the subscript for oxygen. Well, we don't write ones, so I leave the 1 off, and I get NO2. And that's the empirical formula for this compound. Any questions?